Hi, and welcome to your Properties of Organic Compounds podcast. We're going to go over all the different properties that organic compounds have. Before we jump into the properties of organic compounds, it is really important for us to define what organic chemistry actually is. So let's start from the beginning. Organic chemistry, known to the cool kids as OChem, is the study of carbon-containing compounds. So if a compound has carbon in it, we can consider that organic. I want you to take from your mind that layperson term of the use organic, like we would see when we go to the grocery store and we buy organic fruits and vegetables. That's not necessarily what we're talking about here. They stole that term from us. So as far as we're concerned, organic means it contains carbon. And organic chemistry can give us all kinds of different molecules. It can give us oral contraceptives, plastics, antibiotics, synthetic heart valves, you name it. Organic chemistry contributes to the medical field in so many different ways. Here are some of my favorite contributions of organic chemistry to my everyday life. Your upper left-hand corner is the structure of methane, and methane is a component, the main component of natural gas. And as you remember from your first semester chemistry, we know that it burns in the presence of oxygen in a combustion reaction. Ethanol, another one of my favorite organic compounds, is the alcohol that's present in wine and beer and every other alcoholic beverage. It's the drinking kind of alcohol. Caffeine is another example of an organic molecule. We probably all wake up with a little bit of caffeine or have caffeine throughout the day. Notice that we have all nonmetals in the caffeine molecule, and it's very complex. By the end of the semester, you'll be a lot more familiar with identifying those functional groups. The last structure that we have is capsaicin down here, and that's a compound responsible for the characteristic spiciness of hot peppers. It's also an active ingredient in topical creams for pain relief. So you might see that in an arthritic cream, and it's kind of what makes that hot or that warm sensation on your skin. All right, so starting off with organic compounds, all organic compounds have to contain carbon. If they don't contain carbon, they're not organic, duh. Most of them are going to contain hydrogen. If you remember back from first semester, we're looking to complete an octet, and for carbon, that means it's going to have 8 valence electrons that it shares with other elements. This could be through single bonds, double bonds, triple bonds, but usually it's hydrogen that rounds that off for us and completes the octet. Carbon can make 4 covalent bonds. If you remember from its Lewis dot structure, it has 4 valence electrons, and each of those single electrons can be shared with another element to create an octet. And again, carbons or organic compounds in general, can contain single, double, or triple bonds. And to your right are some of my favorites, again, organic chemicals. They are everywhere. Benzaldehyde is responsible for the aroma of cherries and almonds, and at some point this year you will get to smell benzaldehyde. Citric acid, another organic compound that's responsible for the tartness of citrus fruits. It's also used as a preservative. If you see citric acid added to something, it's being used as a preservative. Isoamyl acetate is responsible for the odor of bananas, and ethyl butanoate, the odor of pineapples. All right, so just reviewing Lewis structures and drawing molecules from first semester chemistry. So here in ethane, which is an alkane, we use eth as a prefix too, which we'll learn more about later. Ane tells us it's only single bonds. We have carbon bonded to another carbon. That's a single bond, and then hydrogens are going to fill out the octets. Remember, a line represents 2 valence electrons, so 2, 4, 6, 8. That is a complete octet, and this carbon has a complete octet as well. If we were to remove 2 of those hydrogens, we would have single electrons, which can then be shared in a double bond between those 2 atoms, those 2 carbon atoms. Similarly, if we take off the remaining 2 hydrogens, we would be able to form 3 double bonds. We'd have to share 3 pairs of electrons, or 6 total valence electrons, to create a triple bond. One thing I absolutely love about organic chemistry is it's completely systematic. So double bonds are alkenes, and all the names will end with ENE, and triple bonds are alkynes. They all end in YNE. Continuing in our discussion on properties of organic compounds also form non-polar molecules. They can be polar based on differences in electronegativity between the shared electrons. This goes back to our talk on polarity, which was part of covalent compounds back in first semester chemistry. If you're feeling kind of rusty on determining whether something is polar or non-polar, you're going to want to go back and watch the polarity podcast to refresh yourself in Canvas. So make sure that you seek that out if you don't remember how to determine if something's polar or not, because that's very important in this, especially in these first stages of organic chemistry. So because we don't have an ionic bond, a very strong bond from the transfer of electrons, and we have all covalent bonds, these molecules that we're forming have low melting and low boiling points. So it doesn't take much energy for a phase change from solid to liquid or liquid to gas. They also burn very easily. You'll get a chance in lab to light these guys on fire, and you'll see they go up lickety-split. So organic compounds can be isolated from other compounds in nature, or we can synthesize them in lab. Most are insoluble in water, because water is polar and these are non-polar, but they are soluble in organic solvents. So taking us back to our discussion of solubility, like dissolves like. So if it's polar, it's dissolvable in a polar solvent. If it's non-polar, it's dissolvable in a non-polar solvent. Just a review of valence electrons, organic compounds typically have 4 different nonmetals that are found over and over and over again in the most complex and the most simple molecules. And those are hydrogen, oxygen, nitrogen, and carbon, or as I like to remember them, honk. Hydrogen can form 1 bond, oxygen forms 2, nitrogen 3, and carbon 4. And if you remember from their Lewis dot structures, hydrogen has 1 valence electron. It can form 1 shared pair of electrons or 1 bond with another molecule because it's happy with 2 valence electrons. Oxygen starts with 6 valence electrons, so therefore it can make 2 bonds with other molecules. Nitrogen has 5 valence electrons, so it can make 3 bonds or have 3 shared pairs of electrons to get to 8. And we already talked about carbon having 4. The other term that your textbook likes to use is the term heteroatom. Remember that hetero means different. So when we talk about heteroatoms, we're talking about anything that is not a carbon or a hydrogen in a compound or a molecule. So nitrogen would be an example of a heteroatom, or fluorine or chlorine or oxygen, etc. I know it's been a while since we've talked about covalent compounds and their geometries or their shapes, but this is incredibly important for organic chemistry because that determines the shape of your molecules. So you may want to refresh yourself with the Geometries podcast to remember the different shapes of molecules according to the Vesper theory. They're linear, trigonal-planar, tetrahedral, trigonal-pyramidal, and bent. And I've included this nice little table to remind you of what those look like, how many lone pairs they have, and how many shared pairs they have, because that determines the shape of our 3D organic compound. So notice here we have a carbon surrounded by 4 hydrogens, and those are as far apart as those shared pairs of electrons can be because those electrons are repulsed by each other. They have like charges. They don't want to be close, and that creates this tetrahedral shape that we see in methane. There are 4 different types of formulas you can use to draw or represent your organic compounds, and that's going to be the next podcast, but they are the molecular structure, which you guys have done before. There's a structural formula, condensed structural formula, and skeletal formula, so that'll be the next podcast. All right, here we have an example of a complex organic molecule, and this is lidocaine. And you guys may have come into contact with lidocaine at some point in your lives, but lidocaine is a topical anesthetic, and it causes numbness on the skin. So it can be used as an injection, it can be used as a topical ointment. This would be an injection, but here's the structure of it. So all of these little black circles represent your carbons. So here we see double bonds with our carbons. We also see some oxygen molecules and some nitrogen molecules, but look at the shapes around those. If we were to look at one center atom, I can see that this carbon has 1, 2 bonds, has 1, 2, 3 atoms around it, and no lone pairs. So that is a trigonal planar shape. And so we can look at each of these center atoms and determine the shapes on all of these. You would not look at it as a whole and say this is a shape, because it could really be anything. Another example, let's see, right here, this carbon has 1 atom, 2 atoms, 3 atoms, 4 atoms on it. That's a tetrahedral shape. So you would go atom by atom determining what shape it is.